today. Today we're going to tackle this integral right here, which may look very difficult on the outside, but the inside is one of the easiest things you'll ever do. Okay? So let's get to it. First, we're going to start off with the basics. We're going to learn what a Taylor series is. We say that a Taylor series is the sum or is a polynomial to which when the terms approach infinity, it is equal to some function f of x. Okay? And the formula of this polynomial, we say, is f of x, right, is equal to the sum of from n equals 0 to infinity of the nth derivative of f of x evaluated at some constant a, to which the series will be, or the polynomial will be centered at, multiplied by x minus a over n factorial. And my bad, this x minus a is to the nth power. Okay? And I'll show you guys why this works. Say we have some function f of x, right? And we say that is equal to f of x, right? Plus f prime of x, right? Multiplied by x minus a plus f prime of x multiplied by x minus a squared all over 2 factorial, which just simplifies to 2, plus f triple prime of x multiplied by x minus a cubed over 3 factorial, which is just equal to 6, on and on and on. And we'll see why this works. So when we plug in f of a, right, we get that is f of a plus f prime of x multiplied by a minus x, or a minus a, plus f double prime of a multiplied by a minus a squared over 2 plus f triple prime of a multiplied by a minus a cubed over 6, and on and on and on. We see that this is just equal to 0. So this cancels out, this cancels out, this cancels out, and we see that f of a is equal to f of a. So what happens now when we try to take the derivative of it? So let's say we take the derivative of our original function, right? F of x is this function right now, right here. We take the derivative, right? Right, we take the derivative. This is some constant, so this will go away, right? And to now we have f prime of x, where f prime of x will be some constant, right? Multiplied by 1, because This is just x by itself. The only variable here is x, so this will just turn into 1, right? It is to the first degree, is x to the first. And it'll be plus, take the derivative of this, we bring over the 2. The 2's will cancel out, which just gives us f double prime of x multiplied by x minus a, right? Bring over the 3. And now we have f triple prime of x multiplied by x minus a to the second over 2, on and on and on and on. And so when we plug in a, we see again that these terms cancel out. All terms cancel except this, and we get that f of prime of x is equal to f prime of x. And this will work for any derivative that we take, any nth derivative that we take. We will always get that f to the nth derivative of x will equal to the f to the nth derivative of x. Hence, we call this the definition of the Taylor series. So, an easier series that we use, which is a variation of the Taylor series, is the Maclaurin series. What is the Maclaurin series, you say? Well, that is just our Taylor series centered at 0. So we say that f of x is equal to the sum of n is equal to 0 to infinity of the nth derivative of the function evaluated at 0 multiplied by x to the nth over n factorial. This is significantly easier because we don't have to center it at a function, and we don't have to write all that gibberish, and we could just, and it is so much easier to write. So we'll use this Maclaurin series for now, okay? Now, let's approximate some functions with the Maclaurin series. Let's start with e to the x, the Maclaurin series of e to the x. Ready? So e to the 0, right? F of 0, right? Our formula is f of 0, right? Plus f prime of 0 multiplied by x over 1 plus f double prime of 0 x squared over 2, on and on and on. We know that e to the x evaluated at 0 is just 1, right? And then we know that the derivative of e to the x is just itself. So when we evaluate that at 0, we get that is just 1 times x over 1, which is just x. And we do the same thing again. The next derivative of e to the x is just e to the x, and that evaluated at 0 is just 1. So we say that is 1/2. And then we can do that again, and we get that is just 1/6 x. Oh, my bad. This should not be a 3. Whoopsies. This should be a 2. I'm sorry. I just realized that. X to the second plus x to the third, on and on and on. And knowing this, we can make a series out of this to approximate e to the x, and we can say that it is the sum at n equals 0 to infinity of x to the n over n factorial. Okay? So now let's attack this integral, okay? Let's start with this series right here. This series right here. I'm not going to rewrite the series here, but we're going to just know we're starting with the numerator. So let's take the first term of this. So it's 2 times -1 to the 0 power x to the 2 times 0 times 0 plus negative 1 to the 0 x to the 2 times 0 over 2 times 0 plus 1 factorial. We can do some canceling out. This term will cancel out. This is just 1. This is just equal to 1 times 1 over 1 factorial, which is just equal to 1. So we know the first term of this series is just 1, right? And now the next term is, let's see, 2 times negative 1 times to the first power times x to the 2 times 1 times 1 plus negative 1 to the first multiplied by x to the 2 times 1 all over 2 times 1 plus 1 factorial, which is just 3. And that gives us, let's simplify this, to the negative 1. This should be 2 to the negative 2x to the second, right? Plus this negative 1. So plus negative 1 to the x squared over 3 factorial. Just gives us negative 3 to the x squared over 3 times 2 times 1. These 3's will cancel out, and we just get negative x squared over 2. So we know our second term. We know our second term is just minus x squared over 2. And let's do this third term, and then I'm gonna make a very cool comparison, okay? So for our third term, 2 times negative 1 to the second times x times 2 times 2 times 2 plus negative 1 to the second times x to the 2 times 2 over 2 times 2 plus 1 factorial, okay? And when we simplify that, this will just be 1, this will just be 1, so you get 4x to the fourth plus x to the fourth over 5 factorial, which is just equal to 5x to the fourth times 5 times 4 times 3 times 2 times 1. This 5 will cancel out, and we just get x to the fourth over 4 factorial. And this pattern will just go on and on and on and on. So knowing this, let's put this series we have just made all the way up here. Let's just write it all the way up here. 1 minus x squared over 2 plus x to the fourth over 4 factorial plus minus should be minus plus on and on and on, right? And now let's take a look of another Maclaurin series. Okay, so let's look at the Maclaurin series of cosine of x. Okay, cosine of x. Okay, well, we know that cosine of 0, drew theta by accident. Cosine of 0 is equal to 1. So it's 1, right? And that's the derivative of cosine is negative sine. And when we evaluate that at 0, that'll just equal 0. So plus 0 multiplied by x. This term will go away, right? And now we take the derivative of that again, and we get cosine of 0, which is just equal to negative 1, right? And now when we evaluate that, we get negative x squared over 2. You're noticing a pattern, but let's just keep going. Take the derivative of this. That is just sine of x, and when we evaluate that at 0, that'll equal 0. So 0 times x to the third over 3 factorial. This term will just cancel out, right? And so now when we take the derivative of this is just cosine of 0. This just goes back to cosine of 0, which is 1. And we get x to the fourth over 4 factorial, and it just goes on and on and on. And notice how this looks like our series right here. Right. This is just equal to cosine of x. Right. This is just equal to cosine of x. That's cool, right? So now let's look at this numerator series. When we evaluate this numerator series, we'll do the first 3 terms. We do negative 1 to 0, x to the 2 times 0 plus 1 over 2 times 0 plus 1 factorial. And when we simplify that, should be plus 1. We get that this is just x, right? So our first term is x, right? And now when we evaluate this at 1, we get negative 1 to the first times x times 2 to the first, right? Plus 1, right? Over 2 times 1 plus 1 factorial. And when we simplify it, this is just negative x to the third all over 3 factorial. So let's write that term in. X to the third over 3 factorial. And now let's just do the third term, the last term. And that is at 2, so negative 1 to the second times x to the 2 times 2 plus 1 over 2 times 2 plus 1 factorial, and that just gives us x to the fifth over 5 factorial. And that is our third term. And we will just continue going on with this. Hold up. Minus plus, like that. Basically, that is it. And so now let's look at the Maclaurin series of sine of x. And I think you guys already know where this is going. But I'll save us the time of doing all the derivative stuff. It is just x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. Minus plus on and on and on. And this is just equal to this, right? So we know that this is just equal to sine of x, right? This is equal to sine of x. Okay? Now let's look at this. Let's look at this. This might look confusing, but it's okay. We'll use our series to, what do you call it? To figure this out, okay? So remember when we talked about the series of e to the x being 1 plus x squared over 2 plus x to the third being over 3 factorial, on and on and on. What if we try plugging e to the I, or e to the ix, where I is the square root, or is the imaginary unit, okay? We get 1 plus ix plus I squared, or ix squared over 2 plus ix squared to the third over 3 factorial, plus on and on and on. Well, we get to see that this is just equal to 1 plus I to the x plus, oh no, minus x squared over 2, right? Minus x to the ix, or minus ix to the third over 3 factorial. And I'll just do the fourth term for fun. But the fourth term would look something like plus x to the fourth over 4 factorial. And this pattern would just go on and on. Okay? So now, what if we split up our imaginary terms and our real terms? When we do that, we get this. Oops, this should be a minus. Sorry. Should be a minus. And then plus I to the x minus I to the x to the third over 3 factorial plus plus I x to the fifth over 5 factorial, should be minus. And now what if we take out this I? Well, then we get that this is just equal to 1 minus x squared over 2 plus x to the fourth over 4 factorial, on and on. So always keep writing that plus, should be minus plus, on and on, plus I times x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus plus, on and on and on. And when you do that, you recognize that this is just the Maclaurin series for cosine of x, right? And this right here is just the Maclaurin series for sine of x. And so when we do all of that, we figure out that e to the ix is just equal to cosine of x plus I sine x. Let's get rid of all of this and let's write that all up here. Oops, did not mean to erase that. E to the ix is equal to cosine of x plus I sine x. And so now this tells us to evaluate this at pi over 2 and divide it by I. So when we evaluate this at pi over 2, we get that this is just cosine of pi over 2 plus I times sine pi over 2. Well, this is just 0, right? So we get that e to the I pi over 2 is just equal to I, because this is just 1, right? Pi sine pi over 2 is just equal to 1. And now we divide each side by I, and we get that e to the I pi over 2 divided by I is just equal to 1. Wow, let's write that. Let's write that up here. So now, when we rewrite this integral, we just see that this is the integral of cosine of x, right? Cosine of x divided by 1 plus sine of x dx. And now this is just an easy u substitution. Let's let u equal 1 plus sine of x. And then that lets us know that du is just equal to cosine of x, right? Which we have right here. So now we just have the integral of 1 over u du. That just evaluates natural log of u plus c. And the answer, the final answer to this integral is just the natural log of 1 plus sine of x plus c. That you watch this video and how we were able to dissect this very difficult looking integral right here into something so simple as an easy use of. Who would have known that this is just equal to the integral of cosine of x over 1 plus sine of x dx? But that's besides the point. I just wanted to thank you for watching this video, and that's about all I have to say. Goodbye.